Good morning, everyone. Hi, thanks for coming today, and welcome to this session of Workflow Workshops. We have with us Dr. Pati today, and he's gonna give us a brief introduction to the posterior asymptotics, the Bayesian asymptotic. And this workshop will be divided in two sessions, this Monday and the coming Monday as well. We also have a 2-hour session there. Hope to see you all again. Thank you so much, Dr. Pati. It's all yours.
Well, thanks all of you, and it's great to see all of you here. It's been a while. I taught some of you, maybe some more recently than the others. So I'll just touch upon some of the very basic ideas of Bayesian asymptotics and kind of set up the foundation for further reading if you're interested to go beyond what is taught in here. So let me ask, how many of you had seen some amount of Bayesian asymptotics, apart from the central limit theorem or Bayesian central limit theorem that is taught in 632? Okay. Good. So let's go ahead and get started. So the term Bayesian asymptotics is a bit of an oxymoron because Bayesians always believe in doing inference given the observed data, right? And everything or all justification in Bayesian inference back in the 50s, 60s, and so on is based on the observed data at hand more empirically than anything else. But in classical asymptotics, of course, you can talk about consistency of estimators and things like that, which do not really naturally extend to Bayesian inference. So of course, if you think about like summary measures of the posterior distribution as some sort of an estimator, let's say posterior mean or posterior median, then you can talk about like asymptotics of that particular estimator, right? But it doesn't really exploit the full force of Bayesian inference. So let me talk a little bit about the history. So it all started with a very important paper in the Annals of Statistics. It's by Diaconis and Friedman. In the 1986, who kind of like came up with the idea that you really have to study asymptotics of the posterior distribution simply because, I mean, people used to believe before 80s that no matter what prior you're going to take, it's going to be washed away by whatever samples that you would be working with. But it's not really true if you're working in high dimensions or in infinite dimensions, particularly if you're doing non-parametrics. You can have unexpected prior attenuation, meaning that the prior could have substantial impact on your inference. So you have to be very careful about the choice of the prior. So typically for, let's say, regular parametric problems, it doesn't really matter. So no matter what prior you're going to take, eventually, as we get more and more samples, the effect of the prior is going to be washed out, and the inference is going to be essentially like a classical inference, right? But this is not really true in modern like analysis involving high-dimensional data sets or even like infinite dimensional problems. So that's essentially showed in this Diaconis and Friedman paper back in the 1986. And thereafter, I think there has been a surge of interest in this area just to like give a proper framework to study the asymptotics of the posterior distribution. So of course, we have Bernstein-von Mises theorem. So I'll go into the notations, but just to kind of like remind all of us, the Bernstein-von Mises theorem essentially tells you that if you look at the posterior distribution, again, I'll define the notations, but just to kind of like give a brief snapshot of everything. So the posterior distribution is asymptotically close to a Gaussian distribution, which is centered at the maximum likelihood estimate, and the variance covariance matrix given by the inverse of the Fisher information matrix. So in a sense, so as the sample size goes to infinity. So in a sense, I mean, if you think about like Bayesian credible intervals, those would asymptotically match with frequentist confidence intervals, although the philosophy is very different, right? So when we talk about Bayesian credible intervals, it's really the interval that encloses, let's say, 95% of the posterior mass. But when we talk about frequentist confidence intervals, it's really the interval that would enclose the true parameter if you do repeated sampling from the data generation mechanism, right? So there is no true parameter when we talk about Bayesian inference. Everything is based on the underlying data at hand, and then we talk about like posterior distribution and so on. But these guys actually showed that if you do have an underlying data generation mechanism, and if you think about Bayesian estimators as just like some classical estimator, you can have inconsistent behavior of the posterior mean for large problems, large non-parametric problems. Okay. So with this paper, so Dagnis was in Stanford, Friedman was in Berkeley, and so when they were there in Stanford or Berkeley, so there is another guy, probably you have heard of him, Andrew Barron, was there too as a PhD student. And he kind of picked on the idea and started investigating asymptotics of the posterior distribution. Okay, and it was not until 1999, so he worked on it for like around 13 years before he can prove some result about the posterior distribution, particularly because the ballgame is very different when we try to analyze the posterior as opposed to when we try to analyze maximum likelihood estimates. Right? So this is again a very celebrated paper by Baron, Skarvish, and Wasserman. So parallelly, there was another group who actually worked on this area, which is J.K. Ghosh with his then student Subhashish Ghoshal back in the early 90s. And coincidentally, they also published the first paper in 1999. Pretty much the same idea, but they kind of came up with the ideas independently. Okay. So, so as you can see, so it took like a long time before one can really show something about it. And thereafter, this group actually didn't follow up on their result, but of course, this group kept on like investigating further, and they wrote a sequence of papers. And there, I mean, Ghosh is not there, but Ghoshal has like developed a very strong like suite of results for understanding the behavior of the posterior in many problems that we encounter in modern day. Okay. So if you want to know comprehensively about Bayesian asymptotics and all of the developments and up until now, the best book is the Fundamentals of Non-Parametric Bayesian Inference. And this is the first author is Subhashish Ghoshal himself. And the second author is Ad van der Vaart, with whom he kind of followed up on the subsequent ideas. Okay. So I have to warn you that this book is very dense in terms of technicalities. But if you want to kind of read a watered down version of the book, there is actually a lecture note available. So instead of like putting the link, I mean, here, I couldn't remember the link, but let me just share it with Niladri, and he can share it all of you. So this is a much shorter version of this book, like much shorter version of the book with the important ideas there, and it's really fun to read rather than the book itself. It's quite dense. Okay. All right, so let me just say that there is a lecture note here. So there's a bunch of authors. So first one is Bas Klein. And then I think Vandervat is there. I'm just going to write VDV. And the third author is, I think, Harry Van Zanten. So I'm just going to write VZ. Okay. So you can probably Google and find this one out, but I do have a copy. I can share it with all of you. Okay. All right, so this is pretty much the like historical development of Bayesian asymptotics. So now let's go directly into some of the key ideas. So before actually going into behavior of the posterior distribution, I'll talk a little bit about how do we prove consistency of MLE, right? I'll not really go into the details, but what's the kind of the big picture idea. So let's say, just to kind of simplify things, we have independent and identically distributed observations from some probability density or mass function theta, and theta is living in some parameter space. Theta naught is going to denote the true parameter. So we look at the likelihood, which is the product of the density evaluated at the observations. And then we simply look at the maximum likelihood estimate, which maximizes the likelihood over the parameter space, right? So now the question is, how do we actually prove that theta n hat converges in some notion? I mean, either almost surely or in probability, whichever way you want to call it. So why this is going to happen? So if you recall some of the 613 lectures, so the way that we kind of prove it is the following. So we can also write theta n hat as argmax 1 over n ln theta, where ln theta is the log likelihood, right? And then why this would converge to theta naught? Simply because if you think about it, so 1 over n ln theta, by strong law, this will converge almost surely to the expectation of log of the probability density for one particular data, because these are all IID. And the expectation is with respect to, so again, I'm switching back and forth between F and P. So just to kind of like be consistent, I'll put P there. So 1 over n ln theta will converge almost surely to the expectation, right? So now why the argmax of this guy will converge to theta naught? Any ideas? So loosely speaking, so if you take a look at this quantity, which is the expectation of, so expectation under the true data generating parameter theta naught. So if you expand this one out a little bit, this is going to be simply P of x1 given theta naught log of P of x1 given theta. So when is this guy maximized? So if you think of this integral as a function of theta, so when is this quantity going to be maximized? At theta naught, right? Because can everybody see that? So this is essentially, you can write it as negative of P of x1 given theta naught, and then log of P of x1 given theta naught divided by P of x1 given theta, which gives us the KL divergence. And then we have to adjust for the term that we just introduced here, right? But this additional term that we have in, so can everybody see down here, or maybe this is going to be the limit beyond which I won't really go down. Okay. All right, so as you can see, so this expected value of the log density at one particular random variable can be written as the KL divergence, negative of KL divergence, plus a quantity that's independent of theta. Okay. So if you want to maximize this quantity, that's going to be theta naught, of course, because the KL divergence between P of x1 given theta and P of x1 given theta naught is going to be minimized at theta equals theta naught, so thereby maximizing this quantity. Okay. So now you can see, right? So this quantity converges almost surely to this quantity, and so intuitively, if you take argmax on both sides, theta n hat will converge to theta naught. So that's kind of the big picture idea. Of course, you need to be careful about the details because this requires some sort of uniformity assumption on theta, and just strong law won't really give you. You need a Donsker version of the strong law, which I'm not really going into the details, but intuitively, you just take argmax on both sides, and you will get so this would imply theta n hat converges almost surely to theta naught. So this is basically the proof technique on a very high level when we are talking about consistency of maximum likelihood estimates. Right? Now, when we talk about posterior distribution, the ballgame would be very different because you're not going to work with one particular estimator. So here we are just working with one representative statistic coming out from the likelihood, which is the maximizer. But instead, we are going to look at the entire posterior distribution, and just to come up with the notion when this posterior distribution will converge is a little bit tricky, right? Because we are working with a distribution now instead of just a fixed statistic. So let's now try to develop some of the framework that is needed for studying the consistency of the posterior distribution. Okay, yeah, that's better, I think. Yeah. I'm going to use another one maybe. The rag would be better.
Yeah.
Fine for now. Yeah, thank you. All right, so let's now move on to the actual posterior distribution. So again, IID setting. So we have again independent observation coming from some probability density indexed by the parameter theta. And theta is drawn from some prior distribution pi. And using the prior, we can look at the posterior distribution. So I'm going to use the notation. So let's have a little notation tab here. So x super n is going to denote our observations x1 through xn. Okay. Oh, thank you. So this is going to denote our posterior distribution on the left-hand side. And so how to come up with a notion of consistency of the posterior distribution? So that's our first goal, right? Okay, so now let's draw a brief picture over here. So this is our parameter space, theta. And let's say this is our true parameter, theta naught. So again, we are going to take a frequentist viewpoint when we analyze the posterior distribution. We are going to assume that the true data generating distribution is P with parameter theta naught, which is inside the parameter space. So very simple setting. And then what we are going to do, so this theta, the parameter space, we assume it to be a metric space with some metric D. And then we are going to look at a ball of radius epsilon in this metric D, okay, around theta naught. So this B theta naught epsilon is going to denote the set of all thetas in the parameter space such that D theta theta naught is going to be less than epsilon. And epsilon is just a fixed number to start with. So we are not varying epsilon. So D is a fixed metric to start with. Theta naught is a fixed true parameter. Yeah. So, and this is the definition of posterior consistency. If you fix any epsilon greater than 0, the posterior is said to be consistent at theta naught. So if for any epsilon that you have fixed a priori, the posterior probability of this ball converges to 1, right? So I'm not even like telling anything about the notion of convergence, because we need to talk about what to use, because the left-hand side is a random variable. It depends on your observations, right? So you can look at various notions that you have learned, right? Almost sure, in probability, or in L1. Okay. So let me kind of like talk a little bit about which one typically one uses in practice. L1 is the one that people use in practice. That automatically implies in probability, but not almost surely. So almost sure convergence is typically harder to achieve. So there are some techniques to do that, but again, I'll be mainly focusing on L1 convergence, which makes the analysis really easy. Yeah. So of course, consistency depends on a number of parameters, number of like facts. One is the metric D that you're working with. So if your metric D is a very strong metric, let's say superior metric, then it's harder to achieve consistency. If your metric is relatively like straightforward, like L2, it's easier to prove. Connor, yeah. Right. Right. So right. Yeah, I'm just sweeping some details under the rug. So here, just to make everything formal. So this is the model that you are fitting, right? And this is the truth, which is so this is a truth. And when you're fitting the model, we assume that we know P, but we don't know which parameter, right? So that's the difference. All right, so this is the basic notion of posterior consistency. Again, L1 is what we are going to assume most of the time. So what this would imply? So this implies that if you look at the posterior distribution as a whole, this will actually weakly converge to a Dirac delta measure at the point theta naught. So in a sense, it's not giving us much information, right? It's almost like being a frequentist saying that, okay, I mean, you just forget about the entire posterior distribution because anyway, it's concentrating all its mass around theta naught. Okay. So in this particular sense, the idea of consistency is not very useful because we don't really make any assumption on like this epsilon. Epsilon can be just anything, but it has to be fixed a priori. Right? So in order to make the definition of posterior consistency more finer, so there is a subsequent definition, which is called the posterior contraction rate or convergence rate. And the statement of the this definition is a bit cryptic, but I'll explain all the details. So posterior convergence rate aims for the smallest possible of radii epsilon n, which is converging to 0, such that we still have this statement true. So let me write that down. So is the smallest possible sequence of radii which is going to 0. So epsilon n is a bunch of numbers which is going to 0 with n going to infinity. And we are looking for the smallest. I'll make that clear. Why do we have the smallest? So yeah, Patricia.
So first the definition, they mentioned for any epsilon bigger than
Yes, yeah,
okay.
Absolutely, yeah. If for any right? So why smallest? So we need to have something, right? So smallest possible sequence of radii epsilon n converging to 0 such that the posterior probability of this guy converges, again, let's focus on L1, right, to 1. So why smallest, right? So think about it. So if epsilon is a very slowly decaying sequence of numbers to 0, so let's say 1 over log n, this is always going to be satisfied, right? So if epsilon n is a very sharply decaying sequence of numbers, let's say n to the negative like 100 or something, so then this is never going to be true. The probability would be 0. So there has to be a sweet spot in between for which this result is going to be true, such that if you increase epsilon n further, you'll still have this convergence, but it doesn't give us useful information. But if you decrease epsilon n by a little bit, you're not going to have this. Okay. So epsilon is therefore defined as the smallest possible sequence of radii. Okay. So now this gives us a very cryptic way of defining convergence rate. So typically, how do we obtain epsilon n? Should we just do it for all epsilon and take the infima? It doesn't really make sense, right? It kind of like, sure. Mhm.
And then you have this extent.
Mhm.
So those ends are the same.
Yes.
So each time I'm looking at the different posterior.
Yes.
Different hole, right?
Yeah.
And then
So pictorially, this is what's happening. So n equals 1, you'll probably look at this ball. N equals 2, you're going to look at this ball, and so on.
but I'm using different posteriors on that because you're changing the data.
The posterior, yeah, of course. As n changes, posterior changes.
Yes.
Uh,
So, like, just to understand, it's not
Sure.
like we are working with a one. Like for the first definition, we are working with a one.
Yeah.
I don't care. Like,
Sure.
I'm using more information.
Sure.
Like basically, I'm looking at the measure of that hole.
Mhm.
That posterior.
Yeah.
Posteriors are changed.
Right.
Measure, like I'm looking at the measures. Measures are changed.
Right.
Measure of E.
Sure. So here the set is also changing.
Yeah, exactly.
So you are essentially throwing the posterior more difficult thing to
Yes.
estimate in some sense, right? So the ball is shrinking, the posterior is also like getting degenerate at theta naught. So you can imagine that if you have this epsilon to be too fast, then this is not going to hold, right? Or if you have it too slow, then it's always true. So, right, but you can see this statement is still valid because this is just a sequence of random variables, right? Because this is indexed by the sample size, so there is no dichotomy in the definition.
Yeah. I got it.
Okay. All right, so any questions about the definition? Okay. All right, so we'll move on to some of the more nuanced definition that we find in literature. But before that, let's talk about how do we find this epsilon n in practice, or how do we know that the epsilon n that we have obtained is good enough? We can't really improve it further, right? Okay, so typically there is no way to know, right? So you just have this consistency or convergence rate for some epsilon, and there is no way to know. But it turns out there is a benchmark for any statistical problem that tells you how good epsilon n would be, right? And it's kind of a global fixed sequence of numbers. You just compare whatever you have gotten out of the posterior with that number, and if that matches, you are happy, right? You can't really improve it further. So let's look at that like global benchmark. So this benchmark is given by the minimax rate. So the minimax rate is always associated with a model, which is P of x given theta. The distance that we use to measure discrepancy in the parameter space. So basically these two. Okay, so how this is defined? So this is essentially defined as the following. So epsilon n star is going to be, as the name suggests, it's going to be inf of soup of something. So you are going to look at the worst possible risk that's associated with the distance d. That means you take an expectation under p theta. So that's what we used to denote. Then you look at one particular estimator that's going to be indexed by the sample size. So again, the sample size is always fixed here, okay? So we look at the risk associated with that, look at the maximum risk and choose the estimator from a class of estimators, from a global class of estimators. Let's denote it by C that minimizes the supreme risk. Okay. So this is going to be the minimax rate associated with this particular problem. Theta hat n, right? Yeah. Yeah. And just to give you an example, so so in many problems, there exists an estimator in the global class that you're considering, whose risk matches this epsilon n, right? And you call that a minimax estimator. Yeah, go ahead. Yeah. Right. Yeah. So,
wait. In this problem, the model is something that is fixed.
Yeah. So this is the model.
Yeah, and the maximum is taken over different estimator.
Yes.
Right?
Yeah.
And this one.
Right.
You are minimizing. I mean, this is something, and I mean, I'm just trying to understand what is this thing. Is this estimator, right? This is something that is depend on your.
So it depends on your class definitely, but if you take it sufficiently large, so let's say this is the class of all estimators that you can think about. Okay, so just to make the definition free of the estimators. So this only depends on the distance that you are working on and the model that you're fitting. That's it.
But I mean, typically, say you have something like square error loss.
That would come in the distance. Yeah.
Yeah. No,
Yeah.
I'm just trying to understand what this quantity will be. So this.
Oh, okay. So you will get a number which decays with the sample size, essentially. Yeah. Think about parametric problems. This would be like 1 over root n, essentially. Right? If you choose d to be the L2. Okay. Yeah, just to give one example of this. So we consider the sparse mean vector estimator. So what we mean by that, our problem is the following. So we have n-dimensional normal distributed as normal with mean mu, which is n-dimensional, and variance covariance matrix identity. And this mu is sparse in the sense that only a fraction of its entries are non-zero. So we define a class called the L0 sparse class, which is the set of all n-dimensional vectors with at most s many non-zero entries. So which is x in Rn such that x, the zeroth norm of x is less than or equal to s. This is just counting the number of non-zero entries. Okay. So if you look into this particular class, then what you can prove is epsilon n star. And of course, we need to fix a distance here. So distance between, let's say, any estimator mu hat and mu is going to be 1 over n, the L2 norm between mu hat and mu square. Okay. So if you use this distance, then the minimax rate is going to be S over n log of n over s. Oh, it's just counting the number of non-zero entries in X. Okay. Yeah. Yeah. It's not too easy actually. So there are techniques to achieve minimax or calculate minimax rates, which are given by 3 lemmas: Fano's lemma, Sud's lemma, and something else. And yeah, the techniques vary from problem to problem and distance. Yeah. But this is like the bread and butter of frequentist people, because there's nothing Bayesian here, right? So just to get some intuition of why this S over n comes up. So let me just, yeah, go ahead. So this is the 2.
Right underneath sparsity vector estimator. The mu and the normal.
Oh, I'm just denoting the dimension. Sorry. Yeah, yeah. N by 1. Yeah. Okay. All right. So so can anybody tell why we have S over n here? So let me just, I mean, if I tell you, so there is a true mu naught, right? If I just tell you that the 0 locations of this true mu naught, what's your best bet? So let's say we want to estimate mu, right? So yeah, well, there is no replications here, just one observation, right?
Expectation will be just like how many non-zeros entries are there. So just many non-zeros.
So we are still not looking at expectations, right? So my question is, so let's say the true mean is just a sparse, and I give you the locations of the sparse coordinates, right? So then I tell you what would be mu hat, what would be your choice for mu hat? What's your natural thought?
Only those y.
Yeah, exactly. You just put all of them 0. And if you just look at the L2 norm, so that's going to give you just S over n, right? Just look at that estimator, subtract the true mean, and then you're going to get S over n. So why this log n over s term comes up? It's because you don't really know the location of zeros, and that kind of gives you some penalty. Okay. Okay. All right. So again, it depends on the problem and the metric, and typically it's not an easy job. People write papers with one particular model and one particular distance. Yeah. All right, so now we have a benchmark to kind of know when we are doing good or when we are doing worse. So with that benchmark, let's proceed on to kind of like, yeah, go ahead. Oh, okay. So very good. Yeah. So why the minimax rate is the benchmark and why you can't really improve on it, right? Okay. So let's say you obtain a convergence rate which is faster than the minimax rate, right? Then you can demonstrate that the posterior mean estimator will have convergence rate which is faster than epsilon n, the minimax rate, which contradicts the fact that it's actually minimax, because it's the best possible one.
So we need to first go to frequency curve.
Right, yes.
It's the thing.
Right.
Convergence rate we take.
Exactly, yeah.
So I'm doing double version.
Well, I mean, people have already worked out this problem. So yeah. Go ahead.
The problem is interesting to get the minimax rate or in particular the estimator which is attaining this limit.
Both are interesting actually. Just obtaining the minimax rate is involves actually getting an estimator, because if you demonstrate an estimator that has this particular rate, then you know that minimax rate is always going to be smaller than that, right?
So no, I'm
Yeah.
like
Yeah.
usually what happens, like people try to get first the estimator, then try to get the rate. Is that way or?
No, it's the other way around. People first aim for the minimax rate and try to propose a lower bound first. Okay, so you need to propose a lower bound that the minimax rate is always greater than this number, and that lower bound calculation is typically hard. Then you get an estimator which gives you the upper bound, and then if they two match, then you call that is the one actually. Yeah, it's pretty hard. Yeah. But you know, I mean, information theorists have worked on this problem for long. I mean, the idea is to kind of consider what is called the least favorable parameters essentially. But yeah, there is a very general technique for doing that. So yeah, like people have worked on for like 20 years or something. So you can imagine. Yeah. All right. So let's look at now, once we have a benchmark in place, let's directly go on to finding the posterior or try to find. So now our goal would be to find sufficient conditions for posterior consistency or posterior convergence rate, whatever. Okay. All right. So now let's first look at the posterior itself. Try to intuitively think about why the posterior will concentrate around theta naught, and then we'll go from there. So we'll start with some notations again. We have the notations tab. So we have defined what ln theta is the log likelihood. Go ahead. That's a good problem. Yeah, I know for a fact that there is one model for which the minimax rate is the solution of a differential equation. So it's not really known in closed form.
Case, as you were saying, kind of lower bound of the rate,
yeah,
from your these things, and then you try to match that.
Right. Somehow you need to bring in that complicated equation into the picture, and you don't really get a closed form, but somehow argue that the solution would match. Yeah, I mean, you don't need a closed form all the time. That's my point. Yeah. Okay, so ln theta is the log likelihood, which is the sum of all right. And then we'll also define what is called the log likelihood ratio, because this is another important quantity that would come up all the time. And let's just use ln theta naught to denote that, the log likelihood ratio. Okay, so I'll keep on populating this tab of notation as we go along, but just let's look at the posterior distribution first. And let's say we are doing it for fixed epsilon. It doesn't really matter. And we look for the complement of this. Okay. By definition, it's going to be Okay. So all of you agree with that? So all I have done is like divided the numerator and denominator by e power ln theta naught, which is the true data generating density. So e power ln theta naught is nothing but the product Now let's try to argue why the posterior will concentrate. That means why this probability will go to 0, right? So the basic idea is very easy to understand. So this log likelihood ratio, as theta moves apart from theta naught, is going to be small, right? So what's the expected log likelihood ratio? Typically, it's the negative of the KL divergence. So as theta moves apart from theta naught, on an average, this term is going to be negative, right? So the numerator is going to be small enough. But the denominator, it's an integral over the entire parameter space. So it's not too small. So the denominator is not too small. The numerator is small because we are integrating over a region which does not include theta naught, so which is far away from theta naught. So this would actually force the ratio to go to 0 sufficiently fast, right? So of course you need to work out the details, and the relative balance between the numerator and denominator will tell you what kind of conditions you would need. Okay, so this is the kind of the overarching idea. So now, in order to make our lives really, really simple, I'm going to cheat a little bit, okay? So I'll do it for this very simplified setting where, which doesn't really mimic the reality, but it's kind of a surrogate that you can think about. And then I'll tell you how to kind of like do it for the original problem. Okay, so let's now cheat a little bit. So I don't really now, so whatever be the true parameter theta, I'll not really work with the density actually. So I'll work with a power of the density. So let's say our working model is p to the alpha, where alpha is a fraction. Okay? So this is our working model. So the true data generating distribution is still p of x given theta, because that we cannot raise the truth to the power alpha, because that's not the valid probability model, right? So again, this is not a valid probability density on the sample space, but we don't really care, because we can always like multiply with the prior divided by the normalizing constant. The posterior is always going to be a valid probability density, and that's what we care about. So this is what we meant by cheating. So we are going to see that there is a lot of simplifications because of this fractional power that would give us some insight on how do we show the numerator to be small. So let's look into that. So if this is the working model, so I can look at the corresponding posterior probability, and let's just index it by alpha as well, of this ball around theta naught. And this is going to be simply e power alpha times ln theta theta naught, or complement of that, yeah. Okay. So this is going to be our posterior probability. All right. Okay, so now let's try to argue why the numerator would be small. So I'm going to analyze the numerator and denominator separately here. It might look like that we're not doing something which is probabilistically meaningful, but I'll tie this up together. So I'm going to take an expectation on the numerator first. We can't really do that because the denominator is also dependent on the data. So let's just take a numerator, and we are going to argue that the numerator can be made to be sufficiently small by choosing this neighborhood appropriately. Okay. So right now I have not really decided which D to pick. So the metric is still up for consideration, and our analysis will kind of tell you what metric would give us the right choice to achieve consistency here. Okay. All right, so let's denote the numerator by N, denominator by D. And what I'm going to do now is just take an expectation of the numerator. And remember, expectation always means expectation with respect to the data generating distribution, right? So expectation under theta naught of the numerator is going to be expectation theta naught e power alpha times ln theta theta naught pi d theta. We can push things inside, right? Because this is a positive integrand. Tonally, right? So now let's look at what the inside expectation is. Yeah, go ahead. There should be a. You are right. Yes, I'm dropping the alpha. Say that again.
How do we make that out?
It's not very important. It's just a parameter that helps us doing the computation. So I'll explain in a bit. Okay, so now let's look at the inside expectation. So what exactly the inside expectation is? E power alpha ln theta theta naught. If we expand everything out, so let me do the expectation by expanding every terms out, because I'm just going to do that one time and then kind of hand wave from next onwards. So expectation with respect to theta naught, because we are taking expectation with respect to n many random variables. So the integral, there will be n integrals, and with respect to product measure, right? E power alpha times ln theta theta naught, it's just going to be product p of xi given theta, p of xi given theta naught raised to the alpha. Okay, and then expectation is simply another product with respect to this guy, and then dxi, and the integrals are over the x's actually. Okay, so is the expectation clear? Yeah. So there is an alpha power here that would cancel with, not completely, there would be a 1 minus alpha power there. And because of independence, I can write everything as integral of p of x given theta to the alpha, p of x given theta naught to the 1 minus alpha dx. And because of independence, I'm just going to have raised to the n. Okay. Make sense? All right. Let's use a notation to denote this integral. Okay, so this is free of any kind of data, right? And this just depends on theta and theta naught. So I'm just going to denote this one by a theta naught theta raised to the n. Okay, so question, why is a less than, or a is positive, non-negative, and why is a less than 1? Why? But this is true for any p, right? Holder's inequality, with p being 1 over alpha, q being 1 over 1 minus alpha. So you can prove that a is less than 1, and that's very important. Okay. And of course, in B complement, theta can never be theta naught, right? So we strict inequality.
Why is less than 1?
So this is like f to the alpha, g to the alpha, 1 minus alpha, right? So if you apply Holder,
Okay.
right? So this is alpha to the Holder with p being 1 over alpha and q being 1 over 1 minus alpha. So you can prove that, yeah. Yeah, alpha has to be between 0 and 1. Otherwise, this won't really hold, right? Okay, very good. So then we obtain something like this, and clearly log of a is negative. So you have an exponentially decaying quantity. As theta moves away from theta naught, this is going to be negative, right? So expectation of your numerator is going to be exponentially small. So there is a way to kind of formalize this argument. So the quantity that you're seeing here, there is no kind of like surprise that this kind of quantity appears in the calculations, because this A is like an affinity. It's an affinity between two distributions. It's like the opposite of a metric. And if you convert it to a divergence, that becomes the alpha Renyi divergence. Okay, so let's denote that, define that. So the alpha Renyi divergence between theta naught and theta with an index alpha is simply defined as 1 over alpha minus 1 log of the affinity between theta naught and theta. And it's easy to check that this becomes a divergence, because this is always alpha minus 1 is negative, this is negative, so this is always positive. And also we have the conditions that this is 0 if and only if theta naught is equal to theta. That's easy to prove from the equality condition in the Holder's inequality, actually. Okay, so this becomes a valid divergence, and we can write everything in terms of the divergence, e power negative n times 1 minus alpha divergence between theta naught and theta. It's not symmetric though. Okay, this is called alpha Renyi divergence. Some properties, when alpha equals 1/2, something nice happens. So can anybody see that? So if alpha equals 1/2, this is just square root p of theta and p of theta naught, right? And that reminds us of Hellinger distance. So let's do the math. So when alpha equals 1/2, your affinity essentially is the integral of square root of p of given theta, p of given theta naught, and then Hellinger distance is essentially defined to be 1/2 square root of the integral of square root of p theta minus square root of p of theta naught whole square dx, and this is nothing but 1 minus the affinity. First two terms are just 1 and 1. With the 1/2, it's gone essentially, and the cross product term is giving you the affinity, right? So now the good thing about, so for alpha equals half, what you get here, so let's not do the calculations here. So for alpha equals half, the Renyi divergence becomes d 1/2 theta naught theta becomes, so -2, right? So -2 log of 1 minus the Hellinger square between theta naught and theta, right? And using the inequality, log of 1 plus x is less than x. This is always going to be larger than twice Hellinger square between theta naught and theta. Using log of 1 plus x is less than x for x greater than -1. So we are getting something which is stronger than the Hellinger distance, which is good. We are not getting something which is like completely meaningless, because it's kind of tricky to work with divergences because they are not metric, and since in this particular case this divergence majorizes a metric, it's easy to write down that this is actually less than the Hellinger and just work with the Hellinger itself. Okay. Right. So okay. So this just tells us why the numerator would be small. Then we look at the denominator and then kind of try to argue why it's not too small and then go from there. So let's take a look at the time, and maybe we will just pause for a quick break of 10 minutes if somebody needs to step out. And so the expectation of the numerator is less than or equal to e power negative n times 1 minus alpha d alpha theta naught theta, right? So this is pretty much what we have shown. So now if we choose our d of theta naught theta to be exactly same as the divergence, and then if we construct our ball as the set of all thetas for which d alpha theta naught and theta is less than or equal to, let's say, n epsilon n square, or just epsilon square, then what we have proven is expectation of theta naught of the numerator is less than e power negative n 1 minus alpha epsilon n square, right? So this is just to kind of summarize what we have from our previous discussion. Nothing more we are doing at this point. This epsilon n, we haven't really pinned it down. It's like yet to be determined at this point. But if we consider a neighborhood of this particular size, then all you can show is this part, right? So now our goal would be should I wait for that, or I can go ahead? Okay, good. Okay, so now the posterior probability is nothing but numerator over denominator, right? So we still need to make sure that the denominator is not too small. So up until this point, I haven't really required any conditions. So under practically anything, any condition on the data generating mechanism, if you just choose your distance to be this Renyi divergence, all you can show is the following, that the expectation of the numerator is small. But then in order to show that the denominator is not too small, we need to impose some condition. So let me just ask the question, why the denominator won't be too small? Right, let's look at the denominator. Right. Intuitively, we can understand because this is an integration over all the parameters in the parameter space, and that includes theta naught as well. So we are essentially not making this quantity small, right? But consider the following like weird scenario that the prior itself puts 0 mass around theta naught. What will happen in that particular case? So let's say, and this is a very hypothesized condition. So this is your ball around theta naught. And for some reasons, the prior doesn't really assign any mass around theta naught. Okay. So in that particular case, you can clearly see that the denominator itself would be pretty small because the prior assigns mass outside this neighborhood. And so the log likelihood ratio outside that neighborhood would be small because theta is actually far away from theta naught. And that would essentially kind of make the denominator small as well. But we don't really want that. And that's the reason we need a condition on the prior itself. So now let's talk about what kind of conditions we need on the prior. So conditions on the prior. So loosely speaking, we don't need the prior to have very small mass around the true parameter or 0 mass around the true parameter. And this condition that I'm going to write it down would kind of like make it more explicit. So in order to do that, let's define a neighborhood around the true parameter, which is potentially different from this neighborhood. So this won't really change from problem to problem. So this is fixed. And this condition we would need anyway in order for the denominator to be not too small, because the denominator itself doesn't depend on any neighborhood, right? It's the integral over any parameter in the parameter space. Okay, so now define this neighborhood, which is typically called the KLV neighborhood. So no, I haven't really explained that. Yeah, what I explained is that if the prior is too small or prior is 0 in this neighborhood, the denominator is small, right? Because then the integral is over parameters theta, which is far away from theta naught, for which the log likelihood ratio would be small, making the denominator to be small. So what we need is, we need the product to put sufficient mass in this neighborhood. And then I'm making the neighborhood precise here. And this neighborhood has no connection with the neighborhood that we started with, right? Because the denominator is like free of the neighborhood that I have started with. It's just a integral over the entire region. Okay, so what exactly is the KLV neighborhood? So it's defined as the following. We have epsilon n here and the true parameter here. And this is defined as the set of all parameters in the parameter space for which the KL divergence between P theta naught and P theta is less than epsilon n square, and V divergence, I'll make this formal, P theta naught P theta is less than epsilon n square. Okay. So we all know what the KL divergence is. Just to define it one more time, P theta naught P theta is simply the integral of P theta naught. Again, I'm using this abbreviated notation. I'm using a subscript now, okay? Just to kind of make it less tedious. And the V divergence is pretty much similar, except that we squared the logarithm, okay? And again, all of the reasons why we do this would be clear in a moment when we look at the proof that the denominator is not too small if the prior assigns sufficient mass around this neighborhood. Okay, so here comes the first condition that you need for posterior consistency using this pseudo likelihood with an alpha power. Right? You simply need the condition that the prior probability on this ball should be larger than or equal to e power n epsilon n square. And this is a very, very like important condition. Typically for parametric problems, finite dimensions, easy to satisfy, but it doesn't get satisfied if you are working in like large dimensions. So you need conditions essentially. It says that the prior should not put small mass around that particular neighborhood that we have looked at. Okay. And this is the only condition that would need for posterior consistency. So if you're working on a given problem, I'll work out some examples next week where we'll just verify this kind of conditions. Yeah, go ahead.
This is a function of average sample size.
Yeah, right.
Like if we're assuming that for instance the data set control and M as well, it basically says that requires a lot more slack, a little mass to put on
So the well, I mean, right. So the neighborhood is shrinking, right? And the lower bound is also kind of going to 0. So it kind of balances out. Even if you have a fixed prior, let's say Gaussian with fixed mean, fixed variance, this is satisfied, actually. Yeah. Now, if you want your prior to actually depend on the sample size, then you have to kind of balance it out. You cannot make the variance too small because that would mean that the mass near theta naught would be essentially too small.
Okay, so I guess this N is at sample size.
Oh, sorry. So the N is actually the sample size here, actually. Yeah. But then I think, I mean, typically in practice, we just verify it for a fixed epsilon. And if for any fixed epsilon, you have this inequality, then it's true for epsilon n squared as well. Yeah. So does that answer? Okay. All right. So now let's try to see why the denominator would be not too small under this particular condition. So this is what we are going to show. So we are going to show that with high probability, under p theta naught, the true data generating distribution, the following is true. The denominator, which is e power alpha ln theta theta naught pi theta d theta, is greater than or equal to e power minus a constant times epsilon n squared. Okay. The constant depends on how large probability you want it to happen, actually. Right.
We want to kind of, let's say there wasn't any expectation, we want to show that denominator is not leading the numerator in terms of.
Yeah, that's a very good point. So how can we carefully, both are exponential, right?
Yes.
Denominator is smaller than some exponential. The numerator is also like exponentially small, but we can control the numerator by increasing the neighborhood size a little bit more. So we can beat the constant. So,
Yes.
right, by increasing the neighborhood size by a little bit. That's it. And the reason we want both the numerator and denominator to be exponential, because then we will make sure that our conditions are tight enough. Otherwise, if we don't allow it to decay like exponential, we'll get very strong conditions, which are typically not satisfied in practice. Yeah, go ahead. The constant would be a global constant that would be in terms of the prior mass condition. So we have a condition on the prior, right? So it would be just a global constant. Yeah.
So this is you have this equation of something for something this quantity as
Right.
You want the assumption only on the prior probability of the small ball, right?
Exactly. Yeah.
But my question is that is always this small ball will help you to keep some bound?
Lower bound, right? Integral is always larger than or equal to integral of, yeah.
Lower bound
Yeah.
of this quantity, but you have this your likelihood but still there on that small.
Yeah,
ball, right?
that's why we need this kind of like, so these are properties of the likelihood that we would need. So the proof strategy is that this guy is going to be larger than the integral over this ball, the Bn ball that I defined. And in this ball, the likelihood won't be dominating, essentially.
So the whole point of this idea is essentially to guide your this integral through the prior problem.
Exactly, yeah. But keep in mind that it's not just the prior probability of a neighborhood that depends on the model itself. So we still have the effect of the model, right? It's not just the prior.
But you want the model do not take into like do not affect much, right? That is something.
Right. The analysis actually forces you to do, and so the goal of the analysis is that so you want kind of, so you don't want this term to be dominating, essentially. Somehow you lower bound it with just the prior probability of that particular neighborhood. Yeah.
like, why did you choose this, yield divergence of this various?
The V divergence and the KL divergence, that would be clear once we do the proof, actually. It's heavy shaping inequality. So you need the expectation and the variance, and that's why these two terms come. Yeah, it's just very simple, actually. Yeah. All right, so let's try to go over the proof with high probability under P theta naught, of course, under the prior mass condition. We need the prior mass condition. Okay. Okay, so how to do the proof? So we take, so here is the proof. We take log of the left hand side. Okay. Then we lower bound it with log of the integral on the set Bn. So remember, Bn is the KLV neighborhood, right? It's not the neighborhood that we have started with. So that's very important. So the denominator analysis has nothing to do with the neighborhood that we started with, but it's kind of fixed for every problem. Okay. So I'll go one step at a time just to kind of make sure all the details are in place. So this is fine, right? Okay, so now I would like to apply the Jensen's inequality here. Okay, I want to push the log inside. So what would prevent me to apply the Jensen's inequality? So this probability, this is not a probability on Bn, right? Because the total probability of pi on Bn is less than 1. So we can't really apply the Jensen's inequality. So we make it a probability. We restrict the prior to Bn and then multiply with the probability of Bn. So that comes out of the log like this. Okay. It's a constant. Could be negative or
No, not negative.
yeah, the constant is negative. Yeah. Very good. Okay, so now we can apply Jensen's inequality, and let's kind of rename our prior on the set Bn to be pi n, right? So then this is greater than or equal to alpha times summation I running from 1 through n log of p of xi given theta over p of xi given theta naught pi n. Let's also put a subscript b just to kind of denote that pi is the prior restricted to b. All right. Okay. So now let's take a look at this particular quantity on the left hand side. So this is just a sum of IID random variables integrated with respect to the prior. So we can kind of tell a lot of things about it because it's the sum of IID random variables. We can use our favorite concentration inequality just to kind of tell what would be the variation of this stochastic part, and this part is always going to be lower bounded anyway by the prior mass condition. This is going to be lower bounded by negative n epsilon n square, right? So we can keep the inequality and then n epsilon n square. All right, so how do we apply the concentration inequality? Okay. So we write this as alpha times summation Zi, and then we subtract the mean of the random variables, and then we have to compensate for the mean. And of course, we have the n epsilon n square. Okay. And what these Zi's are? So Zi's are simply one of these random variables. Okay. Integral log of p of xi given theta, p of xi given theta naught, pi nb theta d theta. But these are IIT anyway. Okay, so log of this guy is greater than log. So let's try to apply a concentration inequality now. I'll just keep the last part of the proof. I'll just skip what's there in the denominator. Okay, so let's try to kind of find the probability of dn being, so this is the denominator though, dn being less than some constant times n epsilon n square. Okay. If we can show, sorry, e power constant, or just so remember what we want to prove is d greater than e power negative nc epsilon n square with high probability, right? This is what we want to prove. So we work with the complement, which is probability under theta naught log of d less than negative nc epsilon n square. And then we show that this probability is small. Does that make sense? So we want to show a high probability result on the lower bound of d. That means we want to show a low probability result on the upper bound of d. Okay. All right. So and we know that log d is greater than or equal to the quantity in the bottom, right? So this probability is upper bounded by alpha times summation I running from 1 through n zi minus expectation of zi plus n alpha expectation of z1 minus n epsilon n square. It should be less than negative n c epsilon n square. Okay. It's a bit long, but not too hard to understand. Okay, first question. Can we bound the mean? So z's are random variable of this particular flavor, right? Can we bound the expectation of the z's? Remember, these are probabilities restricted to the good set, right? So once we take the expectation, push the expectation inside the integral, this quantity is always less than epsilon n square because of the construction of b, right? Because this probability is restricted to B. So this guy is smaller than some n epsilon n square. Okay, so we can kind of write this probability as probability of theta naught, of course, with an upper bound, alpha times summation I running from 1 through n, zi minus expectation of zi, smaller than some n times some other constant times epsilon n squared, because we move all of these terms to the right hand side, right? All we have to make sure that the C prime is positive, and that we can tweak with the constant C to make that happen. Okay, so now we are really in good shape. So we have a mean zero random variable, sum of that less than some negative quantity. Any question? So mean zero random variable less than a negative quantity, and this constant is just some arbitrary constant which is positive. So we can even put the alpha here and absorb that in the constant C prime. So if we apply Chebyshev, what kind of bound we'd get? Let's make it unit variance. That would make our life easier. So this is essentially scaled and centered random variables less than a negative quantity. So what does Chebyshev tell you? If you have any random variable with finite variance, then probability that x minus mu greater than some constant times sigma is less than 1 over k square. So this is the vanilla version of the Chebyshev's inequality, right? And you can have replace it by anything like t, you can have t square, but then you have to put the variance of x here. Okay. So all we are looking at is the other negative tail of this random variable, right? So the absolute value is less than this. So this is the negative tail. So this is also going to be less than variance of this guy. And think of this one as your random variable z, right? So then variance of this guy is just variance of these zi's, right? So this is variance of z1 divided by n times epsilon n to the 4. Right? And what can you tell about the variance of z1? Epsilon square, right? So this is good. What we have shown is the denominator is lower bounded this quantity with this probability. So we definitely need epsilon n to be not too small here, right? Pretty much what every epsilon that you encounter in practice would be always larger than 1 over root n. So this will never go to, let's say, infinity or something, in which case we have obtained a vacuous bound. So you want this quantity to go to 0. So the conditions that you need is n epsilon n square should go to infinity. Okay. So if n epsilon n square goes to infinity, and then if the prior mass condition holds, what we have proven is the numerator is small exponentially. The denominator is not too small. It's lower bounded by this guy, e power this guy. And we can make the posterior probability in certain neighborhood to converge to 1, or the complement of the posterior probability, complement of posterior probability of the complement of the ball converge to 0, right? So any questions? So I mean, I haven't really tied up the two things that I have proven. So all I have shown is the expectation of the numerator is small. We haven't really shown that as a random variable, the numerator is small, but you can apply Markovs, right? Since the expectation of the numerator is small, by Markov inequality, the numerator is also small with high probability. The denominator is not too small with high probability. So we take the intersection of these two high probability events, which is also a high probability event, right? If you take the intersection of two high probability event, look at the complement, use the union bound, you can prove that it's also a high probability event. So with high probability, numerator over denominator will be small. That means you have convergence, right? Okay. So how do we choose epsilon? If you are able to find the prior mass condition with the tightest epsilon n possible, that would be our posterior convergence rate. So in practice, what we do, again, this is all about the like model that we raise the, so this is obtained by raising the likelihood to the power alpha, not the standard model. But in this model, what we can prove that if we are able to verify the prior mass condition with some epsilon n, and if you have just this condition, then everything falls in place. But then there would be multiple epsilon n's for which the prior mass condition would be satisfied. How to choose the one that would give us the tightest? So that the minimax rate would be a benchmark for that. We'll start with the minimax rate for the problem. Yeah. You are right. Yes. Yeah. Yeah. It depends on the rate, right? I mean, if it decays, if the variance becomes too small, if a prior becomes overly informative, then there is a problem actually.
So, like I mean, when tackling the denominator, you have to have a good prior, right? I mean, because say you want to achieve some rate.
Yeah.
That,
right.
But your prior is not helping you in this.
That means number 2 is not satisfied, right?
Yeah. So number 2 is not satisfied.
Yeah.
The question is whether we can actually tackle the
Yes.
likelihood in a different way, or because you have this game of these two things.
Right.
This likelihood ratio and your prior, right?
Yeah. So yeah, that's a very good point. I mean, in this analysis, we haven't really talked much about the likelihood, right? It's all about the prior, simply because of the following fact: we are exponentiating the likelihood with the power alpha, making it flat, right? So the prior kind of dominates. But when we do the proof for alpha equals 1 next week, then you're going to see the effect of the prior would come in at a much like stronger rate than this, what we have in here. Yeah. So here the effect of the likelihood comes in only through how the geometry of the KL and the V divergence looks like, essentially. But that's about it. The numerator is small no matter what. If you take any likelihood, raise it to the power alpha, numerator is always going to be small. But that's not going to be the case when alpha equals 1. You need conditions. Yeah.
Just to summarize my
Yeah.
understanding, before you work out a fraction, the numerator is equal to as A, right? And the A, you only show that the expectation for A is small.
Yeah.
But not worked on A.
Right. You just apply Markov's inequality, right? Probability of A larger than some. Yeah.
And so far, you worked on the working likelihood with alpha between 0 and 1, but not taking 1. So how this related to original problem?
Yes, again, as I said, the problem of alpha equals 1 needs a separate treatment. There we are going to see that the numerator may not be small. Just to kind of like tell you one very like easy fact. If alpha equals 1, what's the expectation of e power ln theta theta star theta theta naught? It's just 1, right? So if there is an alpha here, this gives you the exponential decay. But if alpha equals 1, it's just 1. So our proof technique won't really work for alpha equals 1. So there we need to kind of have kind of borrow techniques from hypothesis testing literature, because it's a likelihood ratio. When will likelihood ratio gives us the most powerful test? So you need conditions like that.
Yes, David. And if this technique with alpha less than 1 is not going to work in the original problem, why we are still talking about?
No, because the denominator still remains the same. It doesn't really matter.
Okay.
Yeah. And typically with alpha less than 1, with very like loose assumptions on the model and the prior, you're able to show convergence rate, which is true because it's a more robust model in some sense. Yeah. So alpha less than 1 has certain like implications about robustness, because you're not really using the likelihood, you're flattening out the likelihood. It has some robustness properties. Yeah.
Also include 1, or just the
No, robustness means you're faithful to the data genetic mechanism, right? Yes, yeah. Again, when I'll do the proof for alpha equals 1, everything would be kind of like more clear. And the effect of the, particularly one very important effect of the likelihood will come in is the identifiability. Right now, we are not assuming anything about the model being identifiable or not. There can be multiple parameters that would lead to the same value of the likelihood, and still you have the convergence rate. But when alpha equals 1, it's not really the case. Okay, so I'll stop here and we'll continue next week. Yeah.
It's widely used in Bayesian analysis. It's